So in this second lecture, I'm going to try to talk about the computational models that are used to explore the concepts that Vasan described in his first lecture. To draw information from the light field, from the radiance, and to use it to measure properties of tissue that give diagnostic information and also therapeutic information. My talk, however, will focus on stochastic methods, not to the exclusion of other methods, but certainly it'll be dominated by what I say about those. So let's take a look, as Vasan did, at the overall outline of what I'll be discussing. So first I'll introduce the ideas of forward and inverse RTE, radiative transport equation problems, and remark that they're very different from a theoretical and a practical point of view. I'm going to show you what I call the computational landscape of our field across spatial scales, which is the emphasis in this short course. Then I'll talk about basic forward analytic solvers and prototype radiative transport equation problems. Vasan already described those at the end of his lecture and during the earlier part of it as well. So it'll just be a brief reprise of what he said. We'll present the pros and cons of standard diffusion theory and higher order solvers, PN as he called them, and we'll re-examine the basic types of forward problems. Then we'll go into the stochastic solver ideas in Monte Carlo simulation, and I think the main point of that part of the lecture will be to emphasize that while Monte Carlo simulation done naively is very easy to do and very common, unfortunately it's often inadequate for describing the kinds of problems we want to solve, and it suffers from high error, statistical error. So in order to overcome those limitations of what I'll call traditional or conventional Monte Carlo, we need to find other ways to formulate the problem and solve it stochastically. And so I'll be talking some about that. It's a huge field in itself. It's also important to ask, how do we know that the Monte Carlo simulation, which is following the physics as faithfully as we think it can, how do we know that that is solving the transport equation in the sense that, as Vasan pointed out, the primary need is for weighted integrals of the radiance. So on the one hand, you have an analytic function, an integral of a function that you know times the radiance, and that's the measure you want to extract from the light field. And on the other hand, you're generating photons randomly and counting them in a certain way. How do you know that those two give you the same thing? It's a kind of a fundamental issue. Not a lot of attention is paid to it, I think, in literature. There are very few problems in radiative transport theory that can be solved in closed form, but in one dimension there is such a problem with an exact solution, and any problem that satisfies the transport equation and has an exact solution plays a role as an important benchmark for any other computation you do, and for the Monte Carlo itself, of course, in debugging the code. So they're very, very important, and I'll talk about this one a little bit. Then I want to begin to sort of stretch our thinking over the whole 5 days and talk about inverse problems. Inverse problems are problems wherein, can you hear me? I don't know why, because the mic came off. It doesn't stay there. Like, yeah, put it that way. Try something. Is that better?
We don't use it for amplification, just for recording.
Well, yeah, I just want to make sure people. So inverse problems are problems where we want to discover the properties of the tissue we're interrogating from measurements we make of the tissue. So we're going backwards from measurements to the input. And that's a difficult problem to solve, but it's the main problem of the field, really. It's the fundamental issue. We'll talk about that, and Carol in Lecture 8 on Thursday will be talking much more about it, and then I'll summarize and see whether we've covered the ground. So here there are two basic kinds of problems that interest us. One is the forward problem, in which you start with the optical and physiological parameters. Do we have another laser pointer? Well, so you start over here with the input to the problem, the optics, the optical properties. You assume they're known, and you move through a particular optical model, looking for, that's not the one with the cover. Oh. We'll get it. So you start with the assumed known optical properties, the data that informs the solution of the equation you're solving, whether it's radiative transport, standard diffusion approximation, or the EM, Maxwell's equations, and you get measurement predictions. The measurement predictions are found then by solving the particular equation, diffusion or transport or Maxwell, and using the radiance, the L function, under the integral sign with that multiplier that's known. The detector function is extracting the information. And you make measurement predictions, and that's the forward problem. The inverse problem, as I said a minute ago, is to go in the opposite direction. So you start with measurements, you have the same optical model, and you want to infer the parameters that drive the transport equation. You want to know what's going on, under the surface of the skin. So green arrow points this way, comes back this way. And the inverse problem is an inverse of, I've called it F, the general problem, forward problem, and F inverse is the inverse problem. Now, what we see is that the inverse problem is ill-conditioned. That means that there might be no solution to it, or there might be several solutions to it. For those of you who know a little bit about standard diffusion, you know that in standard diffusion theory, you can't separate the scattering coefficient from the anisotropy G. that they always appear in the solution as the product of mu s and 1 minus g. And so you can play games mu s versus g, or 1 minus g. As long as that value is held constant, you're not going to change the solution in standard diffusion. So if you're using a diffusion model, it's quite clear that you can come to multiple solutions. You can also find no solutions. That means the trouble lies ahead. So to put it in some more familiar setting, maybe, this is an abstraction, but nevertheless it can be made rigorous. If you're given the input here in green, consisting of the geometry, all these other conditions, and you want to determine the output, which would either be the full light field, the radiance L, and or a number D of detectors of measurements like this. F is the detector function. You may have a bunch of them. You may have one. So the forward problem takes you from I to O, and the inverse problem takes you back. And the statement that the forward problem is well posed comes from the fact that the norm, in some sense, of the forward problem is less than 1. You should think of it, interpret that as in this way. Since we have absorption in light transport, and we don't have any generation of light transport other than, say, fluorescence, which we're not counting here. In a single transport equation, you have absorption, you have scattering. You don't have other results competing. So you have an attenuation of the light field, which means that it's a contractive map, the map that takes you from I to O. This one reduces the light field. Okay, there you're taking something away. That means the norm is less than 1, and that is provably tells you that you have a unique solution and that it's expandable in a certain infinite series, which I'll talk about in a moment. However, going the other way, this is not the case at all. The norm of the inverse is greater than 1, and that definitely says that it's a bad problem. It's an ill-conditioned problem. So we have lots of indications that the inverse problem is going to be the real meat of our work. This is an old map of the spatial scales of current optical imaging techniques. On this axis, we're plotting the field of view in millimeters. So going from very small, the less than a scattering mean free path, you have a microscopy in this range, and you have OCT, and you have those that penetrate tissue only shallowly. So the question is, in this we have depth of penetration of the light. Over here we have the field of view. And the map shows you what the properties are as you go in this direction. So you get higher resolution, but more superficial measurements with OCT, and you get a very small field of view, typically. If you want high functional content, if you're predicting optical properties, and you want a deeper tissue measurement, then you're in the high scattering to absorption region, and you'll use photon migration awfully. DOSI technologies, where the resolution is in the few millimeters. But you get low resolution with that, and you have some issues of approximation if you're talking about Maxwell's or even radiative transport theory. In between, you have a large number of applications that require a wide field of view and modest depth penetration and some functional sensitivity in non-homogeneous tissues. So you have all these skin monitoring, preclinical animal models, cortical activation, burns, endoscopic imaging. Those all require a wider field of view and at least some depth penetration. And those are the areas where many of you are working in spatial frequency domain imaging, for example. That captures that area. And Monte Carlo, as we'll see in the next slide, covers quite a lot. Here we have the Maxwell equations in the coherent regime, as it's called, up here at the upper left corner. Radiative transport embraces and includes diffusion theory in the limit. High scattering and low absorption will produce a solution function, the radiance, which is nearly spherically isometric, but not isotropic, I should say, but not entirely, because you always have the source and you have sinks and you have boundaries. So even then, it is not exactly giving you the same result as diffusion. But transport is fairly accurate in spite of the discussion about in the last lecture, down to a mean free path, scattering mean free path, and gives you reasonable depth sensitivity. I mean, it describes depth penetration as far as the light will penetrate. So we tend to spend a lot of time, especially here, investigating better methods to do Monte Carlo simulations. Now here I'm going to revisit the stack of software called the Virtual Tissue Simulator that Vasan mentioned. The problem definition layer of it establishes the input. And the first laboratory this afternoon will have you using a GUI of the VTS in which you explore tissue absorption and scattering spectra. And you recall the last part of Vasan's lecture when you look at that. The solver layer here picks the model that you're going to use to solve the problem, and that'll produce the solution, the radiance, or some approximation of it, of course, and weighted integrals of the radiance that give you fluence, reflectance, and that describes the output. So these two layers are things that we will have labs about this afternoon. But here we're going to focus on Monte Carlo solvers, and the second lab this afternoon uses the Monte Carlo solver panel and has you illustrating various features of the simulation that I'll be talking about this morning. So put that aside for a moment. I've tried to give you a landscape portrait of the field of computational biophotonics. Now I'm going to switch gears a little bit and take a quick look at analytic solvers like standard diffusion in nice geometries. So if there are any questions about what I've said so far, I'll be glad to try to answer them. Okay. So this is a quick look, as I say. If you have an analytic solver, that means that you have an exact solution to a specialized set of equations. For example, it might be only valid for homogeneous or layered tissue. It might, the main one is standard diffusion approximation. That leads to analytic solvers, and you have fast formula-driven computational algorithms as a result of that. So it's amazingly popular and has been for a long time. In all fields of engineering that I'm familiar with, where transport is a phenomenon of interest, the start in the field has been with diffusion theory, and for good reason, because it's easier to solve. One of the problems with it is, of course, you don't know what the approximation error is in general, and in fact, it's even difficult to estimate. So if you're using, say, standard diffusion to estimate the solution, the radiance, distribution, the approximation error, A tilde minus A, where A is the rigorous solution, it's difficult to estimate. And so it's not easy to know, to have evidence of how bad an error you're making with it. But nevertheless, as I said, diffusion-based solutions are still heavily used in biomedical applications and in other engineering as well. Still taking a quick look. In order to obtain closed-form solutions with SDA, you have to restrict to simple geometries and boundary conditions. Otherwise, you can't solve the problem analytically. It does, in those cases, produce fast and formula-driven solutions. And it's most accurate when μs prime, which is this combination of the scattering coefficient and 1 minus g, is dominant over absorption. So these are heavily scattering media. Also, where depth penetration is at least as big as 1 over the transport mean free path. 1 over the transport cross section. So that's the transport mean free path, the inverse. And the big deal about SDA is that if there is a lot of directional dependence in the radiance, you won't be able to capture that with SDA. SDA is a P1 approximation, so there is an isotropic component of the solution, and there's a linear in the cosine of the angle, and that's all. So you have the first 2 moments of the angular distribution, and that is the extent to which you have variation of direction possibilities with SDA. Let's take a first look at stochastic solvers in contrast with what the analytic ones I just mentioned. Monte Carlo simulation produces statistically fluctuating solutions, AN bar, plus or minus some statistical error. Here, sigma would be the standard deviation after n samples. These are statistically varying solutions of the exact RTE equations. So they follow the physics of the radiative transport equation faithfully in the cases that I mentioned where you verified that that is so. And that means that the sample mean, the sample average of the n photons that you've used to represent the problem in Monte Carlo converges to the true solution as the number of particles n simulated goes to infinity, and in that case sigma n goes to 0 as well. The error goes to 0. So the more photons you run, the smaller is the error and the more reliable is the estimate that you get from it. Of course, the figure of merit for Monte Carlo is usually taken as the product of the number of photons times the variance, the square of the standard deviation, and you take the inverse of that. So the larger n is, the larger this combination is, the smaller would be the FOM. If you have, what's worth pointing out here is that this product is roughly dimensionless. It has, since n, the time varies with n. The more you double n, you double the time you've used, and the statistical error is a second moment kind of variation, and so these two, sigma n squared, goes down like 1 over n. And so the product behaves roughly constant in n. So you should notice one thing about your Monte Carlo simulation, and that is the relative constancy of this product of n and the variance. And that dimensionless feature is dimensionless, but the variance, standard deviation, goes to 0 very slowly, as you know, with conventional Monte Carlo. It's of order 1 over square root of n, square root of the variance. So that's a quick look at stochastic solvers. And what else about them? There are no restrictions on complexity of the problem. For example, it can be heterogeneous. The geometry can be kind of wild, as long as you can approximate it with shapes correctly. The Monte Carlo can solve that problem. And the accuracy increases with increasing n, as we saw on the last slide, but convergence is slow. However, the error is easy to compute. At least you know that although it's a statistical uncertainty, you can get estimates of it very, very quickly. And it's used in a standard way as gold standard for RTE solutions. So when people want to compare or validate their technology, they'll compare it with Monte Carlo most often. Now here are some ideas taken, just repeating really what Vassen said, but I want to state that this average behavior of a stochastically varying ensemble of particles. So when you think about solving the RTE equation by Monte Carlo, you should not be thinking of particles that are fixed in space, nor should you be thinking of particles that are somehow regularly spaced, uniformly spaced. You need to think that the population you're interrogating is changing, and it itself has a variance associated with that fluctuation. So you're solving an exact equation, you're solving it in a statistical way. And the forward problem takes the constants that describe the optics and the single scattering phase function P and the source to determine the radiance. That's the forward problem. It generates, how does it work in the simplest case? You can, of course, launch a photon biography according to what the source distribution tells you. So you would normalize that, make sure its integral is 1, and sample from it in a well-known way by generating random numbers and setting them equal, in this case, to the negative logarithm of the random number. Then that determines intercollision distances, applying Beer's law, where the average distance traveled between interactions of any kind would be 1 over mu t. And so you're sampling an exponential with a coefficient, an exponent of minus mu t. Then after sampling such a distance, you will apply the scattering phase function to determine how the direction changes at that location. And mu zero here is not the same mu, not any of these mu's, but it's the cosine of the angle between the initial direction and the final direction. That's the scattering angle. And then after the launch and the first transport and the first collision, you iterate this process. You sample again another distance from the same distribution, you sample another direction, and you continue until the photon either leaves the tissue of interest or it's absorbed. And that would be a kind of a conventional simulation. Just do the physics. Just follow it as faithfully as you can. But it's not the only way to solve the RTE equation, as we'll see in a moment. Now, Boston mentioned that when you want to extract information from the radiative transport equation solution from the radiance L, you do so by multiplying F by a detector function that restricts the light field at which the measurement is taken to certain locations, R, and orientations, directions, omega, and times if it's a time-dependent problem, that are either inside the tissue, in the case of therapeutics, where here there's a target and you might be looking at the fluence or the absorption rate, mu A times the fluence at this target to discover heating and so on, or on the tissue surface here, as in diagnostics, and there, those of you who are familiar with reflectance measurements or transmission measurements would be putting your detectors on the surface and drawing information about the light field between the source and the detector. So those are a reiteration of the problems that Boston mentioned. A manifestation of the spatially resolved case is this one, where you look at simply the light field that's reflected, the reflectance as a function of rho, the distance between the source and the reflectance point or the detector. And S2 minus here, S2 is the unit sphere of all directions. S2 minus is just the directions heading out of the tissue. So S2 plus would be the other half of the sphere coming down. So you're just looking at emergent photons from the tissue with reflectance. And this distance rho between the sources and the detectors, as you can imagine, determines really the amount of reflectance. If the distance is large, you can expect that fewer photons will migrate from source to detector. So the statistics will not be as good. If the source and detector are close, then relatively more photons will find their way to the detector and you'll have better statistics. So the source detector distance, the separation between them, is a crucial parameter in reflectance calculations. And typically, if you're using SDA, you will need to have at least a minimal distance between the source and the detector to have any faith in the answer of reflectance given by SDA. If they're very close, then you would not be using SDA. But in practice, you don't put a detector at a point. You collect the light over part of the unit sphere if you have a numerical aperture if you have a fiber optic detector with an aperture. So unless it's fully open, you get fully open case, you get a full hemisphere of entering. In the case of one with a smaller aperture, you get a lesser gathering of light from directions, and relatively small surface areas that include the particular values of source detector separation of interest. So that then the reflectance would indicate that you want to extract the light field at z equals 0. This is the z equals 0 line going in the outward direction, and you integrate over all directions omega and all source detector separations in this little patch of angles delta omega and delta rho of source detector separations. So that's going to be a function of the size of the detection geometry. So that's spatially resolved diffuse reflectance, or transmittance in the case that when the light goes through the tissue and you capture the light all the way at the other end. Time-resolved diffuse reflectance, on the other hand, is that which looks at the light field as a function of time. Time in tissue is equivalent to distance travel, really. So you can think of it as traveling either a smaller or a larger distance from the detector. And if you introduce a pulsed light source, so the light source is being turned on and off, and you collect light that arrives at each position at different times, or equivalently different distances traversed, then you'll get a variety of measurements of the reflectance as a function of time here, as well as rho and omega. And that is useful in other computational platforms. In both cases, it's quite clear, and Vasan alluded to this already in his lecture, that you want to put detectors in locations where they're going to be sensitive to the properties you're trying to extract. So if you're interested in absorption spectra, you'll need to be concerned with where those spectra lie. It's a function of wavelength, for example. And you'll want to also make sure that you don't have an abundance of redundancy in the detector placements in time or in space, because they'll be giving you roughly the same information. You want information that extracts a good spectrum of detail, and you need to place the detectors intelligently to do that. And I think there'll be some discussion of that in Thursday's lecture 8 about inverse problems, extracting optical properties from tissue. Okay, so there is a small number of equations in RTE that can be solved in closed form, and each one of them is really important because there are so few of them, and they're very good as benchmarks for approximate RTE methods or for validating the Monte Carlo code you've written. And it may surprise us that they capture certain features, although they're one-dimensional problems. That means that scattering can only be purely forward or purely backward in a mixture that reproduces the G. They surprisingly well capture features of 3D solutions. So I'm not suggesting they be used for 3D predictions, but I'm just making this remark to show you how useful they can be. And so this family of RTE problems, which is unique in some sense, is described on this slide, and I've omitted all the details here, but to describe the problem, we'll have a slab of thickness here, D, with a source impinging on the left face, and we are interested in reflectance or transmittance through the slab. The input constants are mu A, mu S, D, the thickness and the strength of the source. Let's say it's 1. The optical properties are going to be simulated from this bidirectional single scattering phase function, P of mu. You ask for a probability P sub F of scattering in the forward direction. That means mu is 1. And a probability P sub B that the scattering is in the reverse direction. That means mu is minus 1. So it's this combination of delta functions such that the probability of forward and backward scattering together add to 1. And the difference between them turns out to be G. In other words, if you multiply this function P by mu, the cosine, and integrate that from minus 1 to 1, you will find you get G. And it's PF minus PB. That comes out of this. So you can mock up a given anisotropy, G, using the bidirectional scattering only. Now, what the typical solution, this purple book by Welch and Van Gammert is a standard in the field, and it has a nice description of this problem and its solution. One way to think of it is that you're combining the light field in moving from left to right with the light field moving from right to left. And if you separate those two components, each one is going to have the characteristics of an exponential. But they're going to relate, they're going to be connected with each other because you can have turnaround scattering, back scattering. So you have their coupled system of first order differential equations. So they lead to solutions. L plus is the solution heading left to right. L minus is heading right to left. And so you're in general going to get sum of exponentials with a characteristic decay rate lambda given by the square root of mu A times mu transport. And C, the C's, the constant C's and the D's, of course depend on the input data, but you can extract the values of those constants from the data, solve the problem completely. One of the interesting things about this solution is that the characteristic delay for this RTE problem is this. It's different from the characteristic delay rate for standard diffusion. For that case, there's a 3 here inside. And so if you plot RTE solutions against SDA solutions and go out far enough, you'll see this difference. Nevertheless, despite its simplicity, it's an easy and very useful problem to know about. Now, okay, what do we mean by analog Monte Carlo simulation? Well, in analog simulation, which is also what I described earlier as conventional Monte Carlo, each photon launched from the source represents a unit of radiant energy, and that unit doesn't vary throughout the life of the biography. So either the photon is absorbed ultimately, it's specularly or diffusely reflected, or it's transmitted. Those are the fates, the possible fates of each photon in an analog simulation. So each photon counts a weight of 1. Either it adds to the absorption data, it adds to the reflection data, or the transmission data. That means that it's generating binomial distributions statistically, ones and zeros. And if you've studied statistics even a little bit, you know the binomial distribution has, the probability of success is small, the relative error is huge. And so in the case of estimating probabilities of rare events with this technique, you'll get a very large statistical uncertainty. With analog Monte Carlo, again, you use Beer's law to transport in homogeneous media the exponential from Beer's law in the classical sense just involves mu a. But distances between successive collisions or interactions of any kind are chosen, as I said before, with mu t in the exponent. And that produces the correct total mean free path, which is the inverse of mu t. If your PDF is a constant times e to the minus the same constant times the variable, the average value is always going to be the inverse of that constant, whatever it may be. Changes in direction by the single scattering phase function, it may not be the bidirectional case. It's any three-dimensional case. Could be the Henry-Greenstein function that Vasan mentioned. It could be a scattering phase function that's derived from more like first principles, me scattering, or a combination of me and Rayleigh. It could be any phase function at all, but we know how to sample functions, any function, randomly. And so we change direction. And again, after the launch, you either get absorbed or scattered. When you're scattered, you're redirected, and eventually either you're absorbed or transmitted or reflected. You leave the region of interest. So each biography contributes a tally of 1, either to the absorbed energy, to the reflectance, or the transmittance, and that's analog Monte Carlo. And because it gives you basically binomial distributions and sample averages thereof for their estimates, it will not be very useful. It'll have a high error if P, the probability of success, whatever that may be in your problem, is small. Therefore, it's important to have other than analog Monte Carlo methods available. And one of them, which is quite general, is what I'll call here weighted Monte Carlo simulation. Now here, each photon represents a beam of continuously or discretely varying intensity. So it starts out initially with unit intensity, just as in the analog case. But energy is conserved as it is before, and you launch each photon with a weight of 1. Now, instead of sampling distances to reproduce the correct total mean free path, 1 over mu t, we're going to sample distances to produce the correct scattering mean free path. But in this example, we're going to distribute the absorbed weight continuously along that path segment. So we're not allowing discrete absorption, but rather we're distributing absorption continuously along the length of the track followed. So here's the sampler for distances traveled between collisions, which are scattering collisions. And this weight of absorbed energy density is distributed along the length S. And the complementary weight, which is this, is scattered, making use of the phase function P. So what's happening is that you're saying, oh, I'm losing light all the time. By the time I get to the end of the track of length S, I've lost this much light. It was absorbed along the way. What's left is going to scatter in a different direction. So the weight is constantly diminishing, and the photon biographies, it can be shown, do correctly deposit the right weights for these three same quantities. So now you're not measuring a binomial distribution with sample means. You have a distribution of weights. That's your statistical distribution, and whatever its standard deviation and variance will be is what you'll get. But it will help you avoid some of the problems of sampling with a binomial expectation. I'm going to illustrate this technique with one that is quite useful, called continuous absorption weighting. It's really the method I just described. We only model scattering, and absorption is accounted for using weights. The estimates are made as I showed you just now. So I was describing CAW in the previous slide. And this same method applies with very wide possibilities. You change the sampling description, you change the weight. You're changing the probability structure of the stochastic model, and you change the tally of the photon to compensate for that change. So this is a very, very important phenomenon in designing better Monte Carlo results. So here we have a single set of photon biographies that can be assigned a set of weights to mimic tissue with arbitrary optical properties, layer thicknesses, and so on. And this idea is very crucial to the use of perturbation Monte Carlo, which is studied later again in lecture 8. Here the idea is that you're going to be estimating a lot of quantities from a single set of biographies by changing the weights. You're performing what-if experiments, and you're saying, well, if the optical properties were not what I said they were, if they're something else, then the weights would have to compensate for them, and I get a different weighted estimator. And you get a whole post-computational quick survey of the nearby perturbed optical property output. So it can't be said too easily, but I've tried to suggest what will happen when you learn about it more. Not only can you get a large number of values of perturbations of, say, radiance, you can get all the sensitivities of the parameters with respect to, of the radiance with respect to each of the parameters that's being varied in the perturbation. So those are sensitivities that are very useful in solving inverse problems. Now here's a flow chart, which isn't so easy to see, I'm afraid. It's not very clear. But it compares analog Monte Carlo with weighted Monte Carlo. And if you go through it in some detail, you'll see that it simply changes in that here there's a loop which allows a new photon to be generated whenever there's an absorption, and otherwise you go back to this sampling again. In the weighted Monte Carlo case, there is no absorption possible, and so you continually sample alternately between distances and directions until the particle escapes somewhere, maybe at the detector or not at the detector. If you're keeping track of absorbed energy density, then that's another matter. You're calculating some internal detection with it, and you can do that continuously from the mean free path. Yeah.
In the weighted approach, is there a point where, sorry. In the weighted approach, if you keep carrying this photon and keeps losing power, is there a point where, it's not worth carrying it around anymore, keeping track of it because there's not much power left?
Yes, that's right. This is a phenomenon that is, in many cases, needs to be dealt with through a process called Russian roulette and splitting, another complementary process. What you do is if you know in advance roughly what mean you're looking for, say it's 0.01, and if your weight becomes, let's say, 2 orders of magnitude smaller than that, you play a game of Russian roulette in which you terminate that biography of low weight. If it satisfies the low weight test with a high probability, you terminate with a high probability. With the complementary probability, you could let it continue with a much higher weight. So the weight multiplication factor, if it continues, and the probability of termination are connected in a definite way so that it's a fair game. So that's called Russian roulette. In other cases, if you have sort of the complementary case where you have in problems in which you have internal sources, or in problems in neutronics where you have the possibility of not only absorption and attenuation, but you also have an exponential growth sometimes from fuel material. In that case, you could have large weights. And if you have a very large weight particle, you may want to split it into a number of smaller weight particles and have them carry independent information from that point on. So those are techniques, sort of numerical experimental techniques for dealing with the issue of low weight or high weight. There's a substantial literature, mostly from Los Alamos, on that topic, and they have developed something for their code, MCNP, which is called weight windows, and it's a way of describing values to assign given certain things you can estimate a priori to those parameters, values to those. So I just want to pictorially show you how you would see the difference between analog and CAW, continuous absorption weighting. So here we have 2 problems. In this one, we're generating analog random walks. In this one, we're generating random walks according to the continuous absorption weighting formula. That means that the mean free path here is the inverse of mu t, and here it's the inverse of mu s, and mu s is smaller. So the mean free path is going to be a little larger than it's shown here. In both cases, let's say we have an internal detector. Maybe we're catching fluence in this internal detector. So at the first step, you might notice the difference in mean free path. Here's the second step. where, again, the mean free path, now you've changed direction at the same point and with the same information. And again, you have a longer step over here than over here. Now on the next step, the third step, on the left side, you've decided the photon terminates here because of absorption. That's the analog case. But here we know that doesn't happen, and therefore there will be another event that follows that. So now already at step 4, you've introduced a new photon, n equals 2, launched from the source, whereas you're still working on the original photon here, and now it's changed direction and gotten to this point, and we'll make a success out of this photon, this weighted photon, so it gets captured by the detector. And in step 5 over here, we have the second photon having made its second step. So there are some of the reasons that you might imagine that the greater variety of possibilities available with weighted Monte Carlo and the greater opportunity to do better than binomial distributions. Continuous absorption weighting is such a strategy. It is not always better than analog. You might be curious to know. Carol is the lead author on a paper that was published recently in which CAWs compared with the discrete version of the same method called discrete absorption weighting, where the absorption is accounted for discretely at each scattering event, at each event, and what you do is you cut the weight by a discrete factor, mu s over mu t, and that's scattered, and mu a over mu t gets absorbed at each discrete event. So the competition between those two is described in detail in this paper, and if you're interested in such things, you may want to look that up. JBO? JOSA. It's a JOSA paper in last year, 2 years ago. Yeah, okay. Carol knows the reference. Now I want to talk about this kind of subtle issue. Let me, before I do that, pause and ask about questions so far. No questions? Okay, we'll go on. I mentioned that it's important to understand why subjects like weighted Monte Carlo or even more abstruse ways of simulating to get the solution of a problem are correct, why they give the correct answer. If you think of the weighted integral of the radiance as the correct answer. So I'm going to try to take a different approach than usually I do to get this point across. We start with the integral differential equation in the steady state case, just to make it a little easier. Here is the directional derivative, the cosine of the angle between the gradient and the unit vector. Here's the losses due to interactions of any kind, scattering or absorption. Here's the input, the increased term due to scattering from the light field in other directions into the direction of interest. And here's the fundamental source, Q. And now I'm just reminding you in this one slide of what the definitions are. These terms that I haven't defined were described in Boston's lecture. This equation can be converted, this integral differential equation can be converted to a purely integral equation in a standard way, taking advantage of the fact that this is a directional derivative. So if it's really a one-dimensional differential equation along that direction is a way to think of it, and you can integrate along that direction and get a result which gives you an integral equation. So that's one way to derive it. So you get an equation in which L, the radiance, is the solution, and K is an integral operator defined by a function called the kernel. The kernel K takes you from location r prime and direction omega prime to another direction omega and at a location r. And if you multiply that by L, that is the action, that describes the action of the operator script K on L. So is it clear this is the integral operator takes a function, the radiance, and maps it into another function, which is this integral, which is still a function of r and omega, same two variables, same 5 variables. So integration is a linear operation on L. Okay, with that in mind, S is back in this equation. The source function here is not Q anymore, but it's the first collision density. It's photons launched from Q and carried from r prime to r in the same direction, omega, and this by this exponential transport kernel T. Now it follows from the fact that the norm of K is less than 1. Remember I told you earlier that we have contractive maps here in the forward direction, and therefore if you think of, let me go back to this equation again. If you go back and look at the equation 2, L equals KL plus S. I'm certainly good at wearing out lasers. Anyway, think of that equation as this equation. On the left-hand side, you have the identity minus K acting on L. And on the right-hand side, you have S. So you have I minus K acting on L gives you S. Therefore, L is given by I minus K inverse, or 1 over 1 minus K. Think of it that way. You can't write the inverse of an operator as a ratio. But if you do, if you think of L as a complex number, and you think that if the complex number has absolute value less than 1, 1 over 1 minus z is 1 plus z squared plus and so on. That series converges when the absolute value of z is less than 1. And so does this series that I'm deriving. It follows from this fact, and it can be rigorously shown, that this series of integrals, called the Neumann series, is a good way, in fact, it's the usual way we find the solution of a Monte Carlo problem. We find the radiance by looking at those particles that are transported to their location and direction directly from the source, that's S. Those that are transported to the same collision, same location, same direction, with one intervening collision, that's the second term, then another collision, and then another collision, and so on. So the reason Monte Carlo is successful is because it does not limit the number of terms that it to a truncated version of this infinite series. The term that's being asked to supply information comes up all the way out. There is no determinable upper bound to the number of collisions that Monte Carlo considers. Nevertheless, you can show that with the norm of k less than 1, the process terminates in a finite number of steps with probability 1. Again, you can only make a probability statement. So the computation is, so to say, subcritical. It ends with probability 1. Okay, so now going on with this, what that means, the inverse I minus L inverse gives you this infinite series of integrals. And here's that infinite series of ever-increasing integrals, 2 at a time, where each integral is an integral over 3 variables, 1 and 2 variables in the other case. This is a 5-dimensional integration in general. This will be 10-dimensional and so on. That series representation of it's not I, it's L, I'm sorry. It has this should be an L. Can be interpreted in terms of the Monte Carlo simulation. Again, I repeat, these are photons that arrive at their first collision directly from the source Q. The next term, photons that reach it after twice, and so on. And so here on the right-hand side, you have the elements of the stochastic model. On the left-hand side, you're capturing the solution of the radiative transport equation. So if you multiply this left-hand side and the right-hand side by the function f, the detector function, integrate that, you can also show that series converges. And that's the connection. That gives you the link. So I is the quantity you're trying to estimate. F is the detector function. You multiply that series term by f and add, and you're guaranteed that converges. That gives you the key to the equivalence between the RTE-based analytic model. It's equations. It's the RTE, and it's F, and it's just analytic quantities, and the stochastic model. And so that's a way of making sure, thinking in terms of the Neumann series, and thinking that if you change the fundamental way you sample, as you do when you move to weighted Monte Carlo from analog, what you're doing is you're changing the K factors, which are the analog transmission factors, to other non-analog ones, perhaps, and you're accommodating for that change by changing the weights. Therefore, you get that cancellation and you get the same I. So that's what you have to show if you want to show this connection between the two models. Any questions about that? So in the virtual tissue simulator, you'll find CAW, you'll find eventually other ways, I'm not sure how many there are, of doing the simulation. Carol, maybe I'll ask you. Other non-analog techniques?
Yeah, you can do the discrete absorption medium as well as continuous.
Yeah. But certainly this afternoon you'll be asked to exercise the analog and CAW and compare them and verify cases where the variance, the statistical error is on one side and the other side. Different cases. Okay, yeah.
If you used enough photons in the analog case, I mean, you can get the variance to be the same. Is that correct?
if
Sorry,
you,
if the N was large enough in the analog case, you could reach the variance of
yes,
the
it would
weighted case.
eventually. The variance goes to 0 as n goes to infinity. But the computational efficiency may be much worse.
Do you have an idea of what that penalty or advantage is?
Well, you can estimate, you can't really estimate it because you have to know the variance associated with the CAW calculation. You can estimate the variance associated with the analog as a function of n, because it's just the square root of p times 1 minus p over n. That comes from the binomial formula. But you don't know in general what the variance of the other is. So the runtime of CAW is longer, of course, because there are more collisions made, but the hope is the error will be smaller. And I think very often, except in exceptional cases, I'll say, that turns out to be so. So it'll be computationally more efficient. Any other questions? Basen.
I just wanted to supplement that discussion. So I think one thing that's very helpful, and that is, I think Jerry early in the lecture introduced this figure of merit. And the
Just
figure
a little
of
louder,
merit,
Vasan,
you
please.
introduced the figure of merit,
Yeah.
which was the product, if I remember correctly, of the number of photons or the computation time multiplied by the square of the standard deviation, or it's basically the variance, and then you took the inverse of that. And what's nice about that figure of merit is that you could run two simulations, say analog on one end and continuous absorption weighting, and you don't have to run a lot of photons. Actually, you could just run 10 photons or 100 photons. You'll get horrible variances, but you also know the computation time. And that figure of metric is, he said, it's dimensionless, or I would say it's an intensive property. It's independent of the number of simulations. So that figure of merit will roughly stay the same regardless of how many photons you run, but you can actually see right away in a short simulation of both what is the improvement in computational efficiency of one or the other. And the challenge with that question is that it is very much problem dependent. And I think continuous absorption weighting has probably right now the most traction in our field in terms of Monte Carlo simulations, because it's perceived to have the best figure of merit, because intuitively you say, okay, you're actually continuously depleting the weight of the photon as it propagates, and it's just intuitively, well, that's how the physics works, right? But it turns out that in some cases it's not the best way, and actually discrete absorption weighting is better. And so I think that gets back to Jerry's kind of underlying message, is that there are many ways to run a Monte Carlo simulation that is faithful to this equivalence between the physical model and the stochastic model. But don't let the physics deceive you. There could be ways, non-physical ways, which evade the mathematics, that are more efficient in actually getting the outcome.
I've a semantics question that I'm trying to get my head around. In your analog model, it seems to be based on a probability of a photon being absorbed, not absorbed, transmitted, not transmitted, reflected. That's your binomial distribution. That seems to be a series of zeros and ones. So where does the analog come from?
So you're getting at the use of the terminology for absorbed?
Yeah, well, I'm just trying to get my head around the two different models, and it seems with the analog model, it seems to be based on two states: absorption, no absorption, scattering, no scattering. Whereas the other model seems to be based on a continuum.
Yeah. Yeah. It is.
Yeah. So I'm trying to get. It seems the wrong way around to me.
Yeah. The only thing I could comment about is that it is possible to show rigorously that those two simulation techniques give the same result, that they give the same correct answer. That is to say that unless you examine the absorption map as a function of location, of course you won't get the same result. But in a gross sense, they will give you the same. They're faithful to the transport equation, both of them.
Okay.
So it's an interesting question because, there's no reason to think of absorption in tissue as a discrete event taking place at the end of a track of a certain length. And yet it's also a little awkward to think of it as a continuous attenuation. Well, probably it is more like that because you have a continuous refractive index in the tissue. Lassen has a comment.
Jerry, I think Gordon's question is not so much of the mechanism of the simulation, but rather why is the analog simulation called analog, where it's more digital, it would seem. You have either 0 or 1. Why is it called analog?
Well, it's called analog, I think, because it's supposedly analogous to the physics. It's thought to be, in the literature, the most like the physics describes. So you think of it as a discrete event in that case. Yeah. Any others? Okay, if not, we'll go on. Now this is just a little bit of a reprise before we take a quick look at the inverse problem. I mentioned earlier that the first two stacks here, problem definition and solver, give you this information. You need to describe the mathematical model you're going to use. The analysis layer, this next layer, examines the sensitivities of the forward solution with respect to various parameters. And the sensitivities, the rates of change of the output with respect to the parameters, is a way of understanding the prospects for solving certain inverse problems. So you will want to know how these derivatives inform the solution technique for inverse problem solution. And optimization layer solves the inverse problem. What you do is as you'll see when you get to that part of the course. So again, we're looking at the layers that haven't really been discussed in any detail yet. Yet I would like now to just open the issue of looking ahead to solving inverse problems. There are kind of three major approaches I've listed here. The first is a table lookup approach, which is simple. The second is based on one-dimensional models, and you'll learn a lot more about this on Wednesday, I guess it is, with the inverse adding doubling technique that will be discussed by Rolf. And then finally, in Carol's lecture, you'll learn about stochastic methods that are based on RTE and the perturbation and differential Monte Carlo method, which is the most widely applicable one. So what is, roughly speaking, the problem? Just reviewing here, I said earlier that the standard diffusion approximation equations give you mu s prime back and not mu s and g separately. And I told you earlier that this means that for any mu s g pairs whatsoever, as long as the product of mu s and 1 minus g is fixed and held constant, you'll get identical SDA approximation solutions. So you can use that both advantageously, and yet it offers a downside to the use of SDA. Advantageously, you can use it to kind of orthogonalize the coordinate system in which you describe your inverse solutions. And I think what that means is that separation of the variables that you're trying to identify. In other words, if you're looking for mu s and mu a in tissue, they'll in general be crosstalk between them. So certain values of mu s and certain values of mu a will be paired, and other values will be paired to give you similar solutions. And the way you minimize that crosstalk is by taking advantage of these so-called similarity relations, which hold for all the PN solutions. But nevertheless, because of this, we know we can expect difficulty in predicting optical property values from RTE solutions. So while forward problems have unique solutions throughout the tissue, SDA can't distinguish between the effects of changing mu s and g. And in the higher order PN case, there are similar limitations that are higher order conditions like mu s times 1 minus g, the higher angular moments combine in such a way that they don't affect the solution if you hold them constant. And so you have the inherent ill conditioning of inverse problems. Let me talk very briefly about table lookup. You have a set of input data and output data. You have J, say J goes from 1 to D, D is the number of detectors, and you have OIJ for I ranging over the number of problems that you solve in the forward direction. What you're doing is just repeatedly solving a forward problem with different parameters over and over again. You're building up a table, and then you're finding the RTE solution that correctly or most closely approximates what you've measured. So that's a laborious way of getting an inverse solution. You have to run a lot of forward problems to get one inverse approximate solution. The output could be based on stochastic methods or exact or approximate methods, any method at all. And you locate the inverse solution either by just finding it in the table or doing an interpolation in that table, or by a nonlinear optimization, a least squares formulation. When you want a fast computation, you'll want to use something like SDA because it has the characteristics of formula-based and is very fast. You'll want to make sure you have high albedos, high scattering to absorption, and you can use the RTE for low albedos, whether it's an approximate RTE solution method or Monte Carlo. When you have scattering comparable or absorption comparable to scattering, you want to avoid SDA. And in the SDA case, you'll have the formulas available in the homogeneous or layered tissue cases, and here are references to papers that where you can read about that. It's fair to say that inverse problem solvers based on SDA are very widely used. and they perform well in the regime in which they operate pretty well, the diffuse regime. You need a metric if you're going to decide how good the fit is. So usually you find a relative error of some sort where the calculated value and the measured values are one is subtracted from the other, and the absolute value is taken. You divide by the measured values in both cases. And this assumes that the measurement errors are roughly equal. If they're not, then you should use a weighted least squares. Standard least squares has coefficients of 1 here. So 1 over r and 1 over t are assumed to have the appropriate comparable weights. If they don't, then the variance is associated with the measured should appear in the denominator. That means that if the variance is smaller, you'll have a higher weight assigned to that sum of squares component. And more generally, if you're looking, for example, to find mu A, mu S, and G, and maybe other optical parameters, you minimize this chi-square function, which is the sum of the squares of the differences between the calculated and measured values divided by the standard deviation. All of that gets squared. So that's it's a weighted least squares really, because it has the variance of the measured values in the denominator. So you de-weight the measured values in which you have less confidence. Now, the general approach based on 1D models, exact solutions, when you need a very accurate RTE solution, you can use this method called inverse adding doubling that Rolf will talk about on Wednesday, and which is the subject of this nice paper by Scott Prahl. And it works in layered tissue, and it also works where you have refractive index mismatches in between the layers of the tissue. And so here's the problem, the 1D problem we introduced earlier, where you might think of using that method because we have an exact solution. So here's just a recollection of a slide you saw before. And at the bottom I say, in principle, you could solve directly for mu A and mu S from knowledge of the reflectance, which is the radiance at 0, and the transmittance, which is so the radiance moving left at 0, that's the L minus, and the radiance moving right at the outer boundary on the right, D. You could do that. There are two unknowns and two constants to be determined, and you could do that, but in practice, you'll find that an iterative method is used to do it, to solve it. And so here's how that iterative method behaves. You input the values of mu A, mu S, G, and D, which you know in the bidirectional case, and you non-dimensionalize these combinations of parameters. So you get an albedo mu S over mu T, and the characteristic time tau, which is the product of the thickness of the slab and the total. So this is the optical thickness of the slab. You get measurements. You can take those from the exact solution because you know it, these two numbers. And you can, say, use Henry-Greenstein scattering, if you like. That's this function. The moments of the Henry-Greenstein function, all of them are powers of G. So once you know the G, first angular moment, you know all of the others. They're just powers of G. And then you can find mu A and mu S as a function of the iteration strategy on the next slide. You start by guessing a set of parameters, mu A, mu S. You calculate the reflectance based on that guess and the transmittance from your exact formulas. You compare the calculated and measured values. You form a chi-square, and you repeat until you get a match. And so this is a little computational algorithm which moves rather quickly, can be used to find inverses using adding doubling. And the nice thing about it is it gives the answer for transport solutions, layered transport solutions, and even index mismatched layered transport solutions. So it's a handy thing to know about. The stochastic perturbation method will be talked about in more detail by Carlo. But what you do is you formulate a perturbation model that treats variable input quantities. It uses weighted Monte Carlo. It implements that model by generating a single set of baseline biographies, one set. And it post-processes the stored biographical data from that one data set and uses a least squares optimization to determine the best fitting strategies. So the computational cost is mostly that of the single set of biographies. Much less of it is in the iteration done in the post-processing computation, and the convergence can be obtained with a powerful method, which would be gradient-based, because, as Carol will tell you, we have Monte Carlo estimates of the derivatives, the sensitivities. So those are available, and you can use a gradient-based optimization method, like the Levenberg-Marquardt method, which is the standard one that we use. So that is the extent of my discussion with you today, and it's 12:30. It's about time to eat. Just to summarize, let me see if I feel that you have captured these points. RTE is a stochastic model, very general. The figure of merit measures the computational efficiency of Monte Carlo simulations, and as Vasan pointed out, you don't need to run many n values. You don't need to run a lot of photons, since n times the variance is roughly independent of n. There are many stochastically equivalent simulations based on Monte Carlo, and they all have different FOMs. They have different computing efficiencies. And so it's a puzzle to figure out what you'd like to use exactly. And we here work on kind of conventional ways of coming at this and some unconventional ways in which we adapt the Monte Carlo to the information it extracts from the photons. If you want a fast inverse solution, you can base it on a formula-based exact or a table lookup. They're also fast. But if you want a general solution with any geometry, fully heterogeneous, any refractive indices, then you need a perturbation Monte Carlo calculation, most likely, and it has been used quite a lot. And finally, at the end, when you get to inverse problems, you see we've already talked about sensitivities, we've talked about forward problems, the role they play, and so you use all of the features of the virtual tissue simulator by the time you get that far. So thanks for your attention. I'll be happy to take any last questions you might have.